we're not recording. Is that what you were gonna say?
No, I was gonna say what letter do you use to represent the efficiency?
Eta.
Theta?
Eta. Okay, so basically, guys, sorry for guys that were outside. I mean, people that were watching live, they were able to see it, but I did not record. I think the first, whatever, 5 or 8 minutes. So let me just give a quick summary. I forgot to put the recording. What I was saying is that so far we have studied the first principle of thermodynamics for a cycle. When you go from one point and you end up again at the same point, that means that the total change in energy is 0. And in that case, the equation simplified to Q equal to W or W equal to Q. That basically means that this equation is 100% efficient. All right. So if you think about a power cycle, if you put this amount of, if you put a certain amount of heat, you should be able to transform all that heat into work. Okay. But we know that you cannot have something 100% efficient. And I was saying that this is the figure, most important figure to understand in thermodynamics. Because basically, I started to do the figure. This is your power cycle, which function is to create power, all right? And the amount of heat you can put in will be given from a hot reservoir. So if we eliminate this figure over here, this part over here, this figure will represent this, which means you can transform all the Q sub H into work or power. But in real life, what happens? Any type of system is going to operate between two different temperature reservoirs, one hot and one cold. And actually, the amount of power you can get is going to depend on what is the temperature difference between those two reservoirs. So really, the amount of work you can get is equal to the QH minus Q sub cold. All right? And now we're going to see different function or different cases. So the first one is the power cycle, and I say that generally the efficiency, the efficiency is always whatever you get out divided by whatever you put in. No? So in this case, what are we trying to get out this system? We're going to get out power, okay, or work. So we have work. What do we put into the system? Heat. And that's where we stop, okay? So now let's keep going. All right, so we have it. So we have it, we have right here the W is equal to Q sub heat divided by Q sub C from above, from here. Okay. Divided by Q sub H, which means that the efficiency for the power cycle can be simplified to 1 minus Q sub C over Q sub H. Okay, and if you want, I'm going to give you something now that is for later on. And really, this equation here, you know and understand it now, is everything about thermodynamics. For the ideal case, you could say that this is going to be equal or proportional to 1 over T cold divided by T hot. So this would be for the ideal power cycle. I mean, I know now it doesn't make sense, but really this equation here, right now we're just concerned about efficiency, but this equation here is what the foundation of thermodynamics. And it's not that complicated, no? All right? But we'll see later on, okay? Okay, so here we define a power cycle. What can be another function of a cycle? Instead of creating power cycle, here is not really working too well now because we don't need it. It's been pretty cold. But in the summer, what do we need? Refrigeration cycles, okay? So let's say 2 refrigeration cycle. Okay, we do again exactly the same figure. But this time this would be refrigeration cycle. I'm going to start simplifying a little bit the figure. Okay, this would be operating between a hot reservoir, providing Q sub H. So be careful here. Don't put the direction on the arrow yet, because I wasn't thinking. This is called reservoir. So let's see, what is the function of the refrigeration cycle? Is to put cold into the system. Okay? All right? So in order to put cold into the system, you need to provide work or power to the system, no? Yeah? And in that case over here, so it's one direction flow, so you will go from the system, you will go to the hot reservoir, you will remove heat. So actually here you have the two ways. What are the two ways to cool the system? Will be either you put cold, and the other one will be to remove heat, no? Which will be called a heat pump. But right now, we are looking at what part of the system? We are looking at this part of the system here. So this part over here is what is the refrigeration. So in that case, we need to do again the efficiency. So the efficiency of a refrigeration cycle so this time they use the letter beta, the Greek letter beta. And again, is whatever you get out, but whatever you have to put in, or let's say, get into the system. So in this case, what are we trying to get out? What are we trying to achieve? Is to put cold, Q sub C, into the system, no? So what we're trying to achieve, to get out, is Q sub C. In order to be able Q sub C, what do we need to provide the system with? Power or work? We have here work. And this would be again the same thing. So this will give us that beta is equal to Q cold divided by Q hot minus Q cold. Or in the ideal case, this will be equal to T cold, T hot minus T cold. Okay, again, this will be the ideal refrigeration cycle. Okay, so you see that you don't need to memorize these equations, all right? And now, the last system will be basically kind of similar to this one, what would be the other way to cool this system? Would be to remove the heat from it, no? So I don't know if you have seen, but right now on air conditioner systems in the house, they have two different systems. One is the classic refrigeration cycle, but lately they try to put more heat pump machines because they are a little bit more efficient. Okay? And it's basically the function is the same one. So this is the idealization. So again, let's do the same figure. So this will be heat pump cycle. So again, do a figure of your cycle here. Heat pump. So now I know the direction. This will be Q sub hot into the hot reservoir. And here we are, Q sub cold coming from the cold reservoir. And again, we know we need to provide either work or power to this system. So the heat pump efficiency. All right. So this time, what is the type of this? What is the part of the system we're looking at? This part over here. So it's the top one. Okay, and for the heat pump, the textbook used the letter gamma. So in this case, what are we trying to achieve? What are we trying to get out of the system? We're trying to get out the heat, correct? The Q sub H. And in order to achieve that, what do we need to put in or to get into the system? Power or work. So same as before, this would just be equal to Q sub H minus Q sub cold. Or for the ideal case, this would be equal to T sub H minus T sub C. So this would be ideal heat pump. All right, guys, let's do 26. And this problem, I like it because conceptually, I think it's important. All right. So imagine this one. I don't know if we can read this or not, but it's not that important. What is to me the meaning of this can be represent the following situation. Let's say it's hurricane seasons, and you're almost sure that you're gonna that you're gonna lose power. Okay. So you need to try to make a decision. I need to buy one generator or two generators. Okay? So let's say you need a certain amount of power, okay, to feed your house. And let's say the total amount of power is W sub A plus W sub B, whatever that is. So you look at two options. Is it better to buy just one big generator that will provide the amount of power? Or is it better to buy two little generators okay? Even though this one, you will put them in series, where one will provide work sub A, and the other one will provide work sub B, okay? So which one is better? Which one of these two setups is better? If both of them are possible, okay? So that's the way I understand that problem. Now let's read it. So figure 26 shows two power cycles, A and B, operating in series, with energy transferred by heat into cycle B equal in magnitude to the energy transferred by heat from cycle A. Okay. So basically Q1, Q2, Q1, Q3, okay, Q1, Q3. Determine an expression for the thermal efficiency of an overall cycle consisting of cycle A and B together in terms of the individual thermal efficiency. So basically, they're asking if you know the thermal efficiency of this one and the thermal efficiency of this one, what will be the thermal efficiency of this combined system? Okay? All right, so let's do that. So let's first do the figure. So A, B, 1, 2, 3. Okay. So let me move to a different page. Page 27. This will be problem 286. Okay, so the first one, we had a power cycle A over here and a power cycle B over here. So here they don't do it, but imagine this is getting heat from a hot reservoir here at the top, Q sub 1, and it's going to a cold reservoir over here, okay? And this one is, okay, so let's maybe do it this one here. We don't need this figure, but let's do it this way. So hot reservoir, here let's put a cold reservoir. For which we know this is Q3. Let's say here in the middle there's another reservoir, okay, where this becomes the outside for this one, but this one will also give heat for this one, okay? So it will be, let's say, a middle reservoir. All right, to change a little bit the figure. Sorry, I don't know if it's more clear. So we know this one here is going to generate a work A, and this one a work B. All right, and we want to know if we substitute this by a big generator, that would be, if you want, opening between the hot reservoir here called reservoir. This will create now work equal to this. All right, so here, I guess the way to do this, okay, let's do this one. What we need to find is the efficiency of this cycle over here. All right, in function of the efficiency of A and the efficiency on B. So if we have an efficiency eta sub A and eta sub B. Okay, so before we start this problem, to have a good idea if this is possible or not, what is in general the efficiency of a car, of the engine of a car? Anyone has an idea? It's between 30%, so the maximum will be 30%, no? All right? So, knowing that, So let's say that the efficiency of a generator will be also about 30%, okay? And let's see what happens. Okay, so for this part over here, what do we know? Efficiency A, the efficiency of, let's say, our generator A will be what? What are we trying to get out? Works of A. What are you trying to put in? Q sub 1, no? So you see, again, I don't memorize the equations. Now, the amount of work you can get will be equal to what? Q sub 1 minus Q sub 2 divided by Q sub 1, or this will be 1 minus Q sub 2 over Q sub 1, let's say, okay? Let me do this part in a methodical way. I'm not going to do it fast, okay? I know what I need to solve for, so I could do it now. But let's say I just follow a procedure, which is write down the equations that we know. So this would be the efficiency of A that operates between the hot and the middle reservoir, no? So we deal with Q1s and Q2s. So let's say this will be our equation letter A. Now, what would be the efficiency of our second generator? So this time we'll have eta sub B. What are we trying to get out of this, let's say, generator? We're trying to get out the amount of work W sub B, and what are we putting into the B? We're putting Q sub 2. Now, the efficiency, the work we can get out of the generator 2B will be equal to what? Q sub 2, because right now this middle becomes the hot for this one, yeah? Minus Q sub 3 divided by Q sub 2, and let's say this will be 1 minus Q sub 3 over Q sub 2. And let's say this will be our efficiency for our generator B. Okay? Now, let's move to this one over here. And let's see what will be the combined efficiency. We do exactly the same thing, okay? So, eta AB. What are we trying to get out of the system? Work sub A plus work sub B. What are we putting in? Q sub 1. Okay, so now maybe, you could do it directly, but let's do it slowly. From this figure, what is the work sub A? Is Q sub 1 minus Q sub 2. And same thing as we have over here. And work B will be plus Q sub 2 minus Q sub 3 divided by Q sub 1. You can see right away that the Q sub 2 will cancel out. But you already knew that from this figure, no? Okay, what will be your guess? What is the amount of work you can get should be equal to what? Q sub 1 minus Q sub 3, no? Yeah, so what is that going to give us over here? You see it's going to give us what we were expecting, Q sub 1 minus Q sub 3 divided by Q1. Okay, or we can just rewrite this one as 1 minus Q sub 3 over Q sub 1. And let's say that will be our equation C. mean, really the problem is done over here. From now on, it's just a matter of algebra. So, okay, so we need to rewrite this efficiency in function of these two efficiencies, A and B. So here, what is the ratio that we have? Q3 over Q1, no? Over here, what do we have? Q1, and this one has Q3. So what is the variable we need to get rid of it? Q sub 2, no? Because we want to obtain Q sub 3 over Q sub 1, no? So we have here, we need to eliminate Q sub 2. Can we solve for these two equations for Q sub 2? We equate that, those two equations together. That way we can eliminate the variable Q sub 2 from these two equations. You understand what I'm doing here? I'm going to solve this one for Q sub 2. I'm going to solve B for Q sub 2. I'm going to equate those two expressions. And then I will get one expression that will be just in function of Q sub 1 and Q sub 3. Okay? That I will be able to substitute over here. All right, so let's do that. So let's see. So solving for Q sub 2 in A and B. So let's first do A. So let's see. A, we had that efficiency of A was equal to 1 minus Q sub 2 over Q sub 1. So let's see, here we get that Q sub 2 over Q sub 1 will be equal to what? 1 minus the efficiency of A, or this will give us that Q sub 2 is equal to Q sub 1 minus efficiency of A. Okay? If you want, let's call this one Roman 1. And we do exactly the same thing for B, which will be eta sub B equal to 1 minus Q sub 3 over Q sub 2. So that means that Q sub 3 over Q sub 2 equal to 1 minus eta sub B. But now we need to be careful here because this is reversed. So it will be Q sub 2 will be equal to Q sub 3 divided by 1 minus eta B. Okay, so if we equate these two expressions, so equating so is both of them represent the same expression. We have Q sub 1 minus eta sub A equal to Q sub 3 divided by 1 minus eta sub B. Okay, what are we trying to find? Trying to find the ratio Q3 over Q1 so we can substitute into this equation. Okay, now from this one, we have that Q sub 3 over Q sub 1 will be equal to what? So I need to move this one there, will be 1 minus theta sub A times 1 minus theta sub B. which is equal to what? Equal to 1 minus eta sub A minus eta sub B plus efficiency of AB, no? If I develop this, it will be 1, will be minus eta sub B minus eta sub B plus, yeah. So finally, substituting into C, which is 1 minus Q sub 3 over Q sub 1, you get that the total efficiency will be equal to what? 1 minus efficiency of A minus efficiency of B plus efficiency of AB. Sorry, it's efficiency of A times the efficiency of B. Sorry guys, I did a mistake here on notation. That's why I couldn't. So here 3, what do we have? Is eta sub A times eta sub B, no? It's not a combined. Sorry for that. You see, it's eta sub A, eta sub B. So here's the same thing. Eta sub A, eta sub B. So that at the end we have that the efficiency eta AB, the 1 cancels out, is equal to the efficiency of A plus the efficiency of B minus the efficiency of A times the efficiency of B. Okay, so that is the answer to the problem of the textbook. But now let's go back to our problem about the generators, no? Okay? So let's do some quantitative analysis. So this is not part of the problem, but for us, we're going to do it. So let us assume that the efficiency of our generator 1 is the same as the generator B, so generator A, generator B, and let's say we say is 30%, so that would be what? 0.3. Okay? So if we wanted to have one big generator that would do the same, let's see, where do I have the figure? What should be the efficiency of this one? Okay? In order to happen. So we just made the calculation that the efficiency of the combined one, AB, needed to be equal to the efficiency of A plus the efficiency of B minus the efficiency of A times the efficiency of B. So this will give us what? 0.3 plus 0.3 minus 0.3 squared, which will be 0.09, no? So this will give you what as efficiency? About what, 0.51? Approximately 0.51, approximately, okay, I mean, even though it's that. So now, the question is that possible? So what does that mean? Can you have a generator that is 51% efficient? we just say that the maximum efficiency of an engine is about 30%, no? Okay, so here, if you wanna have the same amount of work or power, works up A, works up B, just using one generator, the efficiency of that generator should be 51%. Okay, which is in this case will be not possible. Okay, so given that, what does that mean? You're gonna have to go buy 2 generators, no? Unless you buy one generator that instead of providing work A, works up B, provide, let's say, a work that is much higher than these 2, no? Yeah? But if you want just one that creates this one should be 51% efficient, which is not possible. So if you just want to use one engine, you're going to have to find an engine that produces a lot more work than the summation of these 2. Okay? All right. Let me organize the pages and we keep going. The other problem, and probably it's the same in another video, but it's a good problem. That's why I don't mind redoing it. Okay, I like these problems. I like problems where you see figures. Okay, a figure is worth 1,000 words, let's say. So let's see what is this problem about. So shown in figure 27, a cogeneration power plant operating in a thermodynamic cycle. So is what type of cycle is this? Power, no? Okay. Cycle at steady state. The plant provides electricity to a community at a rate of 80 megawatts. All right, so it's right here on the figure. The energy discharged from the power plants by heat transfer is denoted by Q sub out, which is here. Of the 70 megawatts, so I guess that's 70 here. Oh no. Of this 70 megawatts, okay, go to the community for water heating, and the remainder is discarded to the environment. So let's say to the environment over here. Okay, the electricity is valued at 0.08 cents per kilowatt hour. If the cycle thermal efficiency is 40%, determine the energy added by heat transfer Q in. So Q in is the amount of heat you need to provide to the power plant. See the rate energy discarded to the environment. So whatever is Q here to the environment, and the value of the electricity. All right, so like always, to me, the most difficult part in any single problem is to do the right figure, because then if you get the right figure, it's easy to get the correct equations, okay, from the right figure. All right, so let's do that. Let's work on the figure over here. Okay, let's go. So 287, am I recording now? Yes. Okay, so 287, let's say there is a power plant over here. So the power plant can be modeled all right, the power plant can be modeled just as a power cycle. So let's say you have your power cycle here. Okay, that you know is getting heat from somewhere. Here, this would be Q dot sub in. They put the dot because we're talking about power, and this will be coming, let's say, from some type of hot reservoir, okay? So they tell us that this is producing power equal to 80 megawatts. So, okay, I could have done maybe another box, but let's just say this one. Now, out of these figures, some of it is going to go Q out here, Q dot out. So we're going to here, let's say from, we'll call reservoir, it doesn't matter what we call it. So out of here, we know that this is cycle there in between. Some of here, 70. Megawatts go here for heating. And here some will go to the, let's call it Q dot environment. I mean, I could have done a better figure to tell you the truth, but let's work with this one. Okay, so part A, what do we need to do? Part A, we need to determine the rate of energy added to the heat transfer, so Q sub in. And we know that the efficiency of the power cycle is 40%. It's on the figure. It wasn't on the text, but it's on the figure. Okay. So we know this power cycle here has an efficiency of 40%. Okay, first thing we need to find is the amount of power or the amount of coil, whatever you want, or the amount of nuclear energy you need to provide, no? To generate the 80 megawatts. So, okay, so I think this is pretty straightforward. What is the definition of the efficiency for this power cycle? What are we trying to get out of the power cycle? We're trying to get out power, no? The 80 megawatts. What do we have in order to create those 80 megawatts? What do we need to do? We need to put heat inside for the value of Q sub in. Okay? In this case, we know the efficiency and we know how much work this is providing. So we know how much heat we need to provide, no? Think about an inverse engineering problem. You need to design a power cycle knowing that you need to generate 80 megapowers for that city. How much heat you're going to have to provide if you know your thermal plant or nuclear plant is about 40% efficient. Okay? So how big should be your nuclear generator? So from here, you can find that the amount of heat to be generated, Q sub in, should be equal to the amount of power produced divided by the efficiency. We can put the efficiency here. So if we do the numerical application, Q dot in will be equal to what? 80 megawatt divided by 0.4 which is 800 divided by 4, so 200, no? This is 200 megawatts. So Qn equal 200 megawatts. Okay, the way I've done here, this is 4 divided by 10, no? So it's 800 divided by 10. 800 divided by 4, 200, no? So part A, you see, it's pretty simple, but you need to have a figure, no, to know exactly where everything goes. Part B, I think we needed to find Q out, no? I don't know, but let's find out. Part B, we need to find the rate energy is discarded to the environment. No, we need to find the Q environment over here. Okay. So we go to our figure, we need to find here the Q environment. Part D. Q environment. Okay, so let's see what we need to do over here. Okay, over here, since we know 70 will go out, basically what will be the Q environment? Q environment will be the difference between whatever is the Q out minus the 70, no? So really what we need to find to solve over here is for the Q out. So solving for the Q out, we know the work, we know the power, we know QL now. Okay, so we can do this. So we know that the power for this cycle here should be equal to what? The Q hot, which we call Q in, minus the Q cold, which is called Q out, no? This is what we did before. So here we know the total work produced and what is Q in that we just calculated. So from here, we have that Q out should be equal to Q in minus the amount of power generated. So again, these terms are not difficult, but you need to have a clear figure. This figure, I can work it out, but I have to be honest with you, I don't think it's the best one, okay? I think I could have done better, but I can work with it. So if I do the numerical application, I find that Q out will be equal to what? Q in, we just calculated to be equal to 200. And the amount of heat going out to the seat is what? 80. So basically, we're going to find that Q out is 120 megawatts. All right, so now, basically now we know that the Q environment, all right, should be equal to what? To the Q out minus the 70 that go back to the city. This is what would be discharged, let's say, whatever, to a river. Okay? So let's say finally, for this section, Q environment should be equal to Q out minus 70 megawatts, which will be 120 minus 70, will give you that Q environment is equal to 50 megawatts. Okay, and now the last part is not complicated, but you need to do it by looking at the units. See if I can zoom out a little bit. Maybe we can see more. All right, so now the last part, what do they tell you? Let's go back to the problem. So for the last part, okay, the The electricity is valued at 8 cents per kilowatt hour. Okay? The value of the electricity generated per year. All right. So, for C, let's say energy value in dollars per year, I think, no? They ask you. Okay, and what do we know? We know that the charge is 0.08 per kilowatt hour. So over here, guys, I did not read probably this is units is 0.08 per kilowatt hour. So yeah, that means that this is not really what we get. What we get is 0.08 per kilowatt hour. Okay. All right, so let's go back to the problem 1 second. And let's read it again. Determine the value of the electricity generated per year. So how much electricity generated per year? Is that 80? So produce 80 megawatts. Okay, but they don't say is this per year or nothing. Okay, so it's 80 megawatts is what is generated. Okay, so let's see, let's just do this one. So the amount of money per year that we're gonna have will be equal to what? We're gonna have 80 megawatts. Okay, so here maybe, all right, yeah. Okay, so let me write everything and then we do the unit transformation. Then we know the cost of this is $0.08 per kilowatt hour. Are you sure this should be multiplied by hours, no? Or not divided? So now if I transform, yeah, that's what I'm just thinking. Now we need to transform that into years. So, yeah, but for the megawatts, yeah, but I'm looking about the years. The years, both of them will be divided, so you cannot be able to cancel one to the other.
It's number of hours per year.
So, yeah, so really, what should be this? This is what we had at the beginning because the way it's written. This should be really 0. It's not equal. It should be 0.08 per kilowatt hour. All at once, okay? Let me pause this and let me solve it with you. All right, so actually we're good. It's me, I was trying to overthink. This is the correct one. So we have to change the megawatts into this, but now we're gonna have to find this, and then we can do that later on. This will be per year, okay? Okay, so now pay attention because of the units. This is in kilowatts, this is in megawatts. Okay, so really this should be equal to what? 80 10 to the 3 kilowatts. All right, and now we know this will be 0.08 divided by kilowatt hour per year. So let's see, per year, what are we going to do here? So will be, yeah, let's see, I can write this down. So will be, let me do it in blue. So we have 24 hours for 1 day. And we have 365 or 364 days for a year, no? Okay. So now you see everything is the units. So I shall put that one in green. So the day will cancel with the day. These hours will cancel with this hour. This kilowatt will cancel with this kilowatt, and we are left over with dollars per year, no? Which is what we're expecting. So you need to be careful here with the units. So we have at the end here that the amount of dollars per year that this produced. Can somebody do that calculation for me, please? So this gives you that actually this power plant will charge approximately 56 millions per year. And here don't forget to put the units of money. So that's it. So again, sorry for this one here. I think the confusion was over here, but you see that if you follow the units, you get to the answer, no? All right. So that'll be all for today.